slides.
Okay, thanks so much. So thanks again. So maybe let's try to move on to the next talk, which is by Dante Kalise from Imperial College. And please, can you try to share your slides? Okay, so the title of the talk is Gradient-augmented supervised learning of feedback control laws for high-dimensional nonlinear dynamics. Please.
Can you hear me? Yes.
Sorry, I can't. Dante, are you here?
Yes, 1 second. Yes, can you hear me now?
Yes, now I can hear you.
Wonderful, thanks. So thanks. Good morning, good afternoon. You remember this pointer? 2 years ago, it used to be a thing for talks. I'm not going to use it, so the colleagues online they can follow a little bit. So these are some results on supervised learning for feedback control laws for Hamilton-Jacobi equations, basically. And this is a joint work with Giacomo Alvi, Vesa Dasmi, Sara Vicevo, and Carl Kunisch, who's going to talk about something similar along different lines anyway on Friday. So yeah. So this is the starting point for this. So what we try to do here is to do optimal control, to do feedback control of very high-dimensional nonlinear dynamics. So you can think about stabilizing a swarm of drones, or for instance, 1,000 drones trying to achieve a formation in space, and of course, avoiding collisions, which is something that has to be guaranteed because of safety standards and so on. So we want robustness. So you want to compensate disturbances, and guarantee, for instance, certain tracking. There has to be real-time computability. So I could afford a very expensive offline phase, but when things come online, depending on the problem where I want to control, I might have just 1 microsecond to act, for instance, in these sort of problems. Or if you think about chemical control, chemical processes control, you might have a few more seconds or minutes. So sparsity of the control action is something that is going to be important, so that at the end of the day, after solving the Hamilton-Jacobi equation and rigorous control law, I effectively have an object that has a very reduced complexity. And of course, in terms of control and machine learning, I would say that the main trade-off that you face is what I'm showing there between a level of automation and how efficient are we in the use of data. So by level of automation, I mean how easily I can just forget about the technicalities of the dynamics that I'm using. So for instance, you think about deep reinforcement learning that is highly automated, but is really inefficient in the use of data. So to train these models, as we heard in the previous talk, might require hundreds of thousands of samples. On the other hand, people coming from control theory, when you know something about your physics, about your dynamics, you can have very, very accurate suboptimal controllers that are purely based on the dynamics and my physical knowledge of the process that I want to control. That's what I call ad hoc design. It's extremely efficient in terms of data. Sometimes I don't even need data other than what's the current state of the system, but they are not automated. So you change the dynamics and you have to start from scratch. And what I will try to show a little bit is a balance between these two worlds in the framework of supervised learning. Of course, by the end of the talk, I will make a mention of how does this fit in, for instance, semi-supervised learning. So we call like model plus data-driven optimization. So I still want to use as much physics as possible, but sometimes to resort to some data-driven element. So I really second the comments of Siarta in the previous talk, in the sense that specifically when we talk about control, doing this data generation is going to be expensive, because this data generation implies solving an optimization problem. So one probably is in a framework where you can just afford a few thousand samples that will take you one day to generate, for instance, even if you parallelize and everything. So I try to, through analysis and PDEs and optimization, somehow to make the most efficient use of the data that you will see. So, but the framework here is really nonlinear optimal control. So we can think about asymptotic stabilization of dynamics. So we have nonlinear dynamical system, so nonlinear ODE system, or that you want to bring to the origin, for instance, in an infinite horizon by optimizing a penalty of the state of the system plus the control energy that you are going to spend. And the standard technique for doing this infinite horizon problem is using dynamic programming. So you work with the value function of this control problem, and this boils down to solving a Hamilton-Jacobi equation. So you might forget this first part of the slides, but at the end, the bottom line here is that all the things that I want to do, they boil down to solve a nonlinear partial differential equation that is in a high dimensional space. And the reward for doing that is that I will recover an optimal control that is a feedback map. So that solves my first challenge, that I need something that is robust, because this feedback map to be implemented only requires an identification of the current state of the system. So as soon as I know where I'm in the physical space, I'm able to find very quickly, after I have computed V and gradient V, I can very quickly solve this optimization in just one microsecond, and then find what is the optimal option for the system at that current state. But it's a fully nonlinear PDE in non-divergence form, viscosity solutions, blah, blah, blah. Of course, you get a global optimal feedback map. So that's the ultimate answer from a nonlinear control viewpoint. And nowadays, of course, Hamilton-Jacobi equations arise everywhere. Like you have Eikonal equations, Isaac's equation, mean field gains, and mean field control, as we saw yesterday. Of course, the gross of dimensionality here is that the dimension in which I have to solve this PDE is governed by the state space of the dynamics that I want to control. What does it mean? That, for instance, if you think about the nonlinear dynamics of, you want to control nonlinear partial differential equations from a dynamics viewpoint, that would be considered an infinite dimensional dynamical system. After you do semi-discretization with finite elements, for instance, in space, this is a very, very large scale dynamical system. Even if you apply model reduction, this is still a large scale system for solving a PDE over that state space. So some things that we have been working is control of Berger's equation, Allen-Kahn equation, nonlinear parabolic PDEs, would say, that have a very, very nice structure. The other issue, of course, if you want to do feedback stabilization, for instance, of particle systems. So I go back to the first slide where I have this form of drones. This could be easily understood like as a 1,000 dimensional system where you have to accurately track positions for each one of these quadricopters. But in other framework, sometimes you don't worry about the optimal tracking of particles. So you can really think about the particle system in the sense that you want to control the Fokker-Planck equation or some non-local variant of it. There's this is by far the most challenging issue if you think about the deterministic optimal control. So people have been working this for ages, since Bellman, on how can we solve these high dimensional dynamic programming problems? How can we solve high dimensional Hamilton-Jacobi PDEs? And then I just list some references from classical techniques to things that we have been using very recently, tensor decompositions, that I have to say that, for instance, tensor train, they scale equally well as deep learning methods, or representation formulas. This is what I'm going to talk today, basically. This dates back from Berzekas in the 90s. It wasn't called reinforcement learning, it was called neurodynamic programming. But of course, you all know the sort of breakthrough by Ehan and Jensen in 2017 for the stochastic control case, or the deep alerting method by Spiliopoulos and Sirignano on 2018. And we have been working along the ways of doing supervised learning. So through samples of optimal control actions, somehow mimic the optimal control that you would get otherwise by solving the Hamilton-Jacobi equation. So it's a bit cheating because it's solving the PDE, but without solving the PDE. So it's a bit of a philosophical issue here. So what do we try to do? First, to define a global approximation of the solution of the partial differential equation. So, and I really am going to do linear regression here. So I'm going to say that my answer is really a linear combination of multidimensional polynomial bases. So I'm working in the dimensions, I define a polynomial basis there, and I just write a linear answer there. Then how do I generate the data to do regression and find these theta coefficients? Well, for instance, for one thing, we have Laxkov formula, for instance, for aconal type equations. This is a very nice framework, say in Hamilton-Jacobi equations. Sometimes for certain Hamilton-Jacobi equations like this one, you have a representation formula. So actually, if you want to record a specific point in the space-time cylinder, you have to solve a convex optimization problem. And that's something that one can argue whether this is feasible to solve in real time or not. It's a bit of a philosophical discussion, because what do we mean that we are solving a PDE when we solve a PDE? Do you really want a grid-based solution? Do you want your neural network? Or is it okay for you if you can fetch any value of the solution of the PDE on the fly by solving an optimization problem that has such a nice structure that you can solve it in real time? Well, it depends what you want to do. If you want to control an engine in real time where you have 1 microsecond to act, this is really not an option. But if you are controlling a chemical process where you have 1 minute to do the computation, maybe this is just enough. But in what I'm going to explain, I really want to use this sort of representation formula to generate what we call synthetic data and then solve a regression to find a compressed representation of the value function. So at the end, after sampling different states and solving a representation formula, I will there in my last line do a regression problem. I will do a regression problem that has some gradients there that I will explain, because this is the efficiency aspect. In principle, if you use the representation formula, you will recover V. But the truth is that when you solve the optimization problem, you are also going to recover gradient of V. And this is something that repeats in different representation formulas. So now we're a bit on a sort of Hermite interpolation framework where you not only have access to the values of V, but you also have access to the values of gradient of V. And this is very nice because gradient of V scales as the dimension. So you have a lot of information from a single sample. So this is what we call a gradient-augmented regression. So I will have samples from a function and its gradient. I will solve a linear least squares problem there, but with a sparse penalization. What is the purpose of this sparse penalization? That I will have as few coefficients there in theta as possible. That will give me a compressed representation of the feedback that will be very effective, or if you want to, or efficient in its true meaning to implement in real time. And I don't have to choose a priori what are these theta. I will just let the optimizer, of course, the sparse optimization determine what are these representatives, what are the relevant representatives there. Of course, the Laxkov formula that I was showing before is for a very particular case of aconal dynamics that they do not relate. They only relate to a very simple time optimal control problem. In the general case, you have this type of control, not the infinite horizon, but the finite horizon deterministic control problem. Nonlinear dynamics, a control entering in a control affine form, right? Linear in the control. If your control is unconstrained, what you have is that the optimal control from the Hamilton-Jacobi equation is really a direct expression from the gradient of the value function, and the value function itself solves this Hamilton-Jacobi equation. So this is sort of a vanilla version of the Hamilton-Jacobi equation that I was showing before, because I got rid of the optimizer. It's just compute explicitly. Now, something that people claim in optimal control that is partially true, and one has to be careful here, is that Pontryagin maximum principle gives you the equivalent of the characteristic curves of this. So Pontryagin maximum principle is necessary optimality conditions for a given initial condition. The Hamilton-Jacobi equation really solves the global optimization problem. So this is a bit tricky. One has to be rigorous when claiming that this system there, this 2-point boundary value problem, corresponds to the characteristic curves here. But of course, the advantage is that this 2-point boundary value problem can be solved independently for different points, for different initial conditions, and then I can use this to generate data for doing a regression and approximating the solution of the Hamilton-Jacobi equation. And actually, this is a nice result. We spent a lot of time finding what was the precise statement. It's not really that you can match sufficient with necessary optimality conditions, of course. So if you go back to one paper by Miris in 85, and this 100-page paper by Suodina is a translation from Russia, you will find the precise statement. Just to make it short, if F and G and L, so the dynamics and the cost are smooth, you can claim that these things, that actually the characteristic shares of the Hamilton-Jacobi equation can be decoupled in solving these sort of 2-point boundary value problems. And this is something for which I tell you, we have solvers, efficient solvers to do the data generation. Moreover, once you solve this problem, you recover V by evaluating the optimal trajectory that gives you the value function, which is the optimal cost. Furthermore, when you compute the gradient of the value function is nothing but the adjoint variable of this 2-point boundary value problem. So by solving one single problem for a given initial condition, I can retrieve the value function and the gradient of the value function along all the optimal trajectory. So it's a lot of data. It's gradient data, value data, and the data in the whole trajectory. But of course, one needs to understand what is the framework where these things hold true, because otherwise you are just approximating the object with the wrong data. Actually, if you go back to this paper of Yegorov and Dauer in 2017, that's a very nice survey, and it is very readable in terms of what are the technical conditions that you need for this to hold true. So what do we do? It's very simple. We just generate a sample of initial conditions. So it's a high dimensional space. For each one of these initial conditions, we solve this 2-point boundary value problem, which we can do by gradient descent, Newton method, or you just use right away a 2-point boundary value problem solver. And then that generates a synthetic data set for the value function and the gradient. I don't want to bother you with how do we treat the time variable, so I'm just assuming that I'm just interested in approximating a V at time 0. That is enough to generate a control that sterilizes. And then I will fit a polynomial model for the value function based on this data and the gradient. So this is a sort of Hermite regression. And I do a lasso regression because I have this L1 penalty. So I don't need stochastic gradient descent. I can use a most beautiful convex optimization framework to do this. Now, people talk a lot about architecture when talking about deep learning, and here why I'm going back to using a polynomial model for a value function. Basically, because there is an extensive and rigorous mathematical literature on power series expansions for Hamilton-Jacobi partial differential equations. And this really dates back to around the same time of Bellman and Galkunis and collaborators and Tobias Wright. They have wrote very nice papers explaining that in certain cases characterizing the solution of the Hamilton-Jacobi equation in terms of power series that are naturally expressed as polynomials. Moreover, there are people working on certain quantification and approximation theory, and actually, all this idea of using the gradient information came from a completely different context, and a very beautiful paper by Benatko and Swin 2019 that is called Hermite interpolation, where they do this lasso regression, but using this very nice problem: recover a function from measurements of the function and its gradient. And the first thing that we are taught when you take an optimal control lecture is that in the linear quadratic case, the value function is in fact a quadratic form. So for the linear case, I can have an exact recovery if I do a polynomial ansatz for the value function. And then I can think that nonlinear extensions would be just the solution of the linear quadratic case plus some additional fellows there. The only thing that I need to, well, now there are two things. How do I solve the optimization? But before that, what is my polynomial basis? Because I just told you that I'm taking a polynomial basis in a high dimensional space. And of course, this wouldn't be effective to really overcome the curse of dimensionality, like people say. Because of course, if you were to take tensor product monomials, this thing will suffer the curse of dimensionality. If you take total degree monomials, so you are just truncating monomials in d dimensions by their total degree, that allows us to scale up to say 14, 16 dimensions, but then it becomes overwhelmingly expansive. Instead, we take what we call this a hyperbolic cross approximation, which is to choose the representative based on the product of the degrees in the monomial term. So I'm playing the game of having a polynomial basis in d dimensions up to degree n. What are these representatives? And in this case, of course, the hyperbolic cross is a much sparser selection of candidates there. So the cardinality of this set really allows me to solve, I don't know, 100-dimensional problems without no much trouble. Of course, at some point it escalates, and then one can make the case of using deep neural networks or something that it can effectively be curves of dimensionality free. And then this is just linear regression. I have my samples, I assemble my matrices, and then I cast my sparse optimization problem there at the bottom. So I really want to find these theta coefficients minimizing an L1 norm, the coefficients of the expansion, plus these matrices that are nothing but the assembly of the sample data of solving these open loop control problems. We use just technicality, we use a weighted L12 norm, and this is inspired, justified by this paper by Atko and Sui, where, well, and some previous references where they advised to do so. And of course, this is a convex optimization problem, non-smooth because of the L1 norm, but we can really use IDMM or for solving this weighted lasso and the shrink operator. And at the end of the day, it's a very nice iterative method. You will recover an optimal feedback law that is sparse. So the Q coefficient there at the bottom, it's really much reduced than if you were taking. So these are my full representatives. I might have a certain number, and through the sparsification, most of these are going to be 0. Most of the coefficients in front of the monomial are going to be 0 because of the L1 penalty. So this Q, I expect it to be smaller than the original basis that I defined. And this is important if you really want to do real-time control. So let me show you just one toy example. It's called the Van der Pol oscillator. So nonlinear, 2-dimensional nonlinear dynamics. You have a linear control entering there. So what you see there on the left is really my sampling data. So of course, I didn't use all this data to do the training. I just use a fraction there. But you sample your open loop control problems, and you see that actually the value function more or less matches with what you have there. So what are the other options here? If you do an L2 regression, you do an L2 regression, this bar, the bar indicates that I'm using the gradient. So if you do an L2 regression without gradient, with say 40 samples, you are really not approximating the right shape. You have all these spurious oscillations. So the regression is really not doing it's not working properly. Of course, this is going to be solved if I increase the number of samples, like in the picture on the right. But as I was saying, each one of these samples requires a solution of these two boundary value problems. So I don't want to go in that direction. It's not surprising that if I increase the number of samples, I will obtain something that is slightly better. What I want to do is to get something more accurate, but with fewer samples. And what we do there then is the gradient-augmented regression. So in each sample, I'm using the value and its gradient, and I'm using this L1 sparsification. So the second picture is a nice one, because now I obtain less error with few samples because I just use for free this gradient information that I received. And because of the L1 penalty, instead of having 52 coefficients, I only have 19. So my expansion of the optimal feedback is something much more compressed that I would have if I just do an L2 regression. And this repeats over and over for different examples. So one example that we're interested in relation to the multi-agents problem at the beginning is, for instance, the Cucker-Smale model for consensus. So you have a particle system where the evolution, the Newton equation for the position would just be an averaging on the velocities through a kernel. You can control each one of the agents. If you don't control them, you can see the trajectories, they will diverge. Through the action of a control, you can steer them to consensus. So I'm really now at the order of 80, 100-dimensional Hamilton-Jacobi equation. And through this idea, I'm able somehow to mimic the optimal state, like in the third picture there. So here again, the comparison, if you were to do the regression with say 2000 sampling points and you don't use the gradient because it doesn't have a bar there, you don't use the gradient, you get this picture of the in the right, that it really means that the control is not very good. So it's not very accurate. It's not making the job of steering the agents towards consensus. Instead, with 70 samples for an 80-dimensional problem, just because I use the gradient, and the gradient now is an 80-dimensional vector. So I'm getting a lot of data from a single sample. I can just do it with 70 samples, find the optimal or something that really mimics the optimal control. Of course, it's not perfect because still there is an error in the regression, but it does the job. So you can see here, so the difference between the top row here and the bottom is that the bottom is not using gradient information. So you can see that to achieve similar levels of error here in the training, you really need a couple of orders of magnitude more samples. So having the gradient really pays off. Having the L1 penalty really guarantees that you will be sparsifying your feedback law. And just to start closing, what has this to do with neural networks? Well, for instance, I've been working with finite horizon control. If you work with infinite horizon control, you don't have such a nice representation formula. You don't have Pontryagin, you have Pontryagin, but it's not a bad idea. It's a very bad idea as a two-point boundary value problem because the terminal condition is going to be at infinity. So forget about Pontryagin if you were to solve the infinite horizon control. You still want to solve this static Hamilton-Jacobi equation, which gives you the optimal feedback in the infinite horizon case. What we know from control theory is that in the linear quadratic case, so the dynamics are ax plus b, the solution to this problem is really solving a matrix algebraic Riccati equation. So you solve for a quadratic form that gives you a value function v, and then gradient v follows and gives you the optimal stabilizing feedback law. Instead, one thing that engineers do for the nonlinear case is what they call the state-dependent Riccati equation. They will just, at every time step, they will freeze the coefficients, they will write the dynamics in semilinear form, they will freeze the coefficients, and they will just solve this Riccati equation and then move along the way in an optimal trajectory. Of course, this has a catch. Well, just to tell you, if you go to MATLAB, you have a solver for algebraic Riccati equations, and it's very efficient, and many people have done a lot of progress over the last 2 or 3 decades on this. So this is a building block that you can rely on. But of course, if the dynamics are expensive, this matrix equation takes a little while. So the way that these things are implemented in practice is that people solve the state-dependent Riccati equation by freezing the coefficients. They apply the control for 1 minute, and they evolve and repeat. The catch here is, of course, this can only be applied to problems where you have sufficient time to do this computation and then go back and provide the optimal action for the next hour or for the next minute. You cannot do this to control an engine in real time because the engine is an action within 1 microsecond or a fraction of a second. This is not the solution of the optimal feedback law. It's suboptimal, but stabilizes. So that's another thing that engineers, mathematicians, or myself, I tend to over-obsess about optimality, but engineers, they are mostly concerned about things that work. Then if you can optimize it and make it nicer, well, that's good for them. But first, things need to be computable and implemented in real time. So here we really do supervised learning with deep neural networks, which is basically sample different conditions, solve the Riccati equation for each one of these conditions, and then solve a supervised learning problem to learn this feedback law. So here I'm not doing the regression. We just give it a try with neural networks for the same consensus problem that I was showing you in the previous example. And then, well, again, this is a one-dimensional problem. You can see in the top row that the uncontrolled dynamics, that they do not go to 0. Then in the bottom row, both positions and velocity of the agents go to 0. The bottom line here is that by wrapping up this controller, this neural network control, by doing this offline training and then doing the online control, for instance, if you were to have a 200-dimensional system, doing this Riccati equation online would require of the order of 12 seconds. By using neural networks, you can really do it like in a fraction of a second. So you are really enable real-time control for nonlinear dynamics through the use of supervised learning. So that's the end, basically. So dynamic programming, Hamilton-Jacobi equations. How can we replace the solution of the Hamilton-Jacobi equation using Pontryagin or things that are well known from the optimal control literature? How far can we go in using high-dimensional approximation with polynomials? Actually, our experience is that by using tensor decompositions and polynomial regression, nowadays we can scale as equally good as using deep neural networks. But of course, there is a world there of things that probably are not solvable with polynomials or tensor decompositions in particular. But on the other hand, there are things that for me, they are not enough from a control perspective. For instance, if you think about controlling swarm robotics, so the level of accuracy that we have training neural networks now is still not good enough to guarantee, for instance, that there will be no collisions in a swarm of drones, for instance. And I'm not going to sell, I don't know if you would buy like a Tesla car with a guarantee that it will not collide up to a certain accuracy. You know, you want the self-driving car that doesn't collide. So there is a world of complex problems where we still need to go a little bit with increase the accuracy to be able to provide controllers that would have a guarantee of performance. And I think that I can close with that. Thanks.
Okay, thanks so much, Dante, for this very interesting talk. Are there any questions?
Wei can raise a hand. Wei ask in the chat. Yeah.
Okay. Hey, Dan. It's very nice to see you.
What time is there, Wei? Huh?
Yeah, it's 4:30 a.m. That's okay. Yeah. Okay. Very interesting that the last part you use deep learning for the infinite time optimal control, right? Infinite time optimal control. And you generate data based on state-dependent Riccati equation. It seems to me that you can also use polynomial representation rather than supervised deep learning using neural network. Is that right? Or I missed something?
No, you're absolutely right. I could have done the same thing with polynomials, but I go back to the previous talk that at some point, as I increase the dimension, these samples are going to become so expensive, these Riccati equations, that I will have to leave the supervised learning framework. And what we are doing at the moment is to work with semi-supervised. So you still would have a residual term of the Hamilton-Jacobi equation coupled with this data. So this is what we're interested in, the supervised learning, because we want to generate data that would complement the minimization of the residual of the PDE. And there we would use neural networks if we scale higher in the dimension. Still, we have a limitation of 100 state variables. And if you think about this drone example, the picture at the beginning, you know, with 10-dimensional quadrocopters, we're talking about thousands of state variables. So it wouldn't be enough with polynomials. Yeah.
One more question, hopefully it's quick, is that you mentioned, you know, in the polynomial representation, you mentioned the basis can be like total degree or the hyperbolic type. If you gave me a system, I take a look. Is there any way I can, you know, kind of tell which set of basis I should use? Because it seems to me the hyperbolic is much more efficient in terms of dimension. But can I tell? Or?
No, I mean, the way that we do polynomials, we do hyperbolic polynomials because this is the only thing that we could do in 80 dimensions. In 80 or 100 dimensions, I couldn't afford the total degree. Of course, the total degree would have more representatives and perhaps. So I guess the right question is when this hyperbolic cross, for instance, would be a bad idea in terms of the underlying dynamics. So yeah, we're assuming that things here are not very anisotropic, that the value function resembles a quadratic form. So it's really not, it's a control affine setting where the dynamics are not going to give you a value function that is very skew or has some anisotropy across dimensions. Yeah.
That makes sense. Thank you.
You're welcome.
Thank you. Are there any more questions? Maybe I'll ask a short question. So you mentioned that engineers are not so much concerned about optimality, but just they just want to make sure that this works. So, and then you said you're going to introduce this penalty to have a sparse solution. So do you have an idea how far away this brings you from optimality?
I mean, okay, just to refine my statement. Engineers, they would care about optimality, but first things that things to be working. So you wouldn't mind having something that is guaranteed to be stabilizing, but is suboptimal. Then there is the real-time implementation. So the real-time implementation issue is solved by this L1. So whatever I solve, yeah, is optimal for the regression problem that I'm solving. How far do I get from the solution of the Hamilton-Jacobi equation? To be honest, no. This is something that I don't know. I don't have a precise estimate for that. Yeah. On the other hand, having an L1 penalty reduces the complexity of my feedback law. So we go back to something that can be implemented in real time. Because at the end, you might have the optimal solution, but the optimal solution might be so complex because it has so many terms of expansion that it's not suitable to be implemented in real time.
Okay, thanks so much. Yeah. And in the beginning of your presentation, you showed pictures of these Olympic rings with drones. And you said that the neural network or your approach is not precise enough to do this. So do you know how they did this?
Yeah, this is centralized control. So they would have, yeah, that's the thing, that you go to industrial control, and actually there's a survey that said, but around the year 2000, like 90% of these devices were just tuned by trial and error. So you have somebody who knows everything about this dynamics, and then they just have what is called PIV controllers or model predictive control, where they just linearize the dynamics and they sample very, very quickly. But this is not by no means a good approximation of the Hamilton-Jacobi equation. Yeah.
Thank you. So are there any other questions?
Okay.
Okay, so then let's thank Dante again for the very interesting talk and all the speakers of this session.